let's wait a few more seconds before we start. Okay, so time is over. We should start. I try to share the screen. So do you see my slides now? Yeah, I see some hands, so at least one, yes, good. Good, and the second thing, I will start recording because last time I have learned there are some messages jumping on me. I don't know whether you do something or not, but the thing is that I have to start the recording myself, because if you do it, it won't be stored permanently. So I have to start the recording, which is done now. And hopefully it works. And somebody write something to the chat. Good. So let's start. If anything doesn't work for you, like you don't hear me, you don't see me, you don't see slides or whatever, just try to let me know. I will try to solve it. And now somebody write something. Everything is fine. Good. So if everything is fine, do not write me. Now, yeah. So last week we finished with basic introduction to the VxWorks operating system. So this week we are going to continue, and do one more change here. We are going to continue, and we will talk more details, and we will also start talking about like practical stuff, how to do this and that in VxWorks, because this is what you will need in labs this week. So VxWorks is real-time operating system. Unfortunately, it's proprietary, but it's like it is, and it has some properties like preemptive scheduling and so on. Last week we have already talked about it. It's useful for a real-time operating system to have preemptive scheduling. You will learn why in this or maybe in next lectures. With respect to intertask or interprocess communication, basically VxWorks offers what all the other operating systems offer. So you can have here things like semaphores, mutexes, message queues, signals, pipes, sockets, shared memory. This week at labs, we will play with semaphores and mutexes. Next week, we will go to explore shared memory. Of course, VxWorks also offer a lot of connectivity solutions, which means like networking IPv4, IPv6. It's a standard today. There is already support for upcoming Ethernet standard or occurring Ethernet standards like time-sensitive networking, USB communication CAN buses, and so on. Again, if you want to survive in today's world of operating system, you have to support this. So this is all supported. We will also play with network communication in the labs. You will use it at least for your semestral work. And then there are other features. Again, it's a must in these days, like multi-core support, virtualization, asynchronous I/O. There are some file systems supported. In terms of file systems, the support is not that rich as in case of typical server or desktop operating systems. VxWorks supports only a handful of file systems, but for embedded systems, this is typically sufficient. You don't need to have fancy file systems for terabytes of storage and so on. At least these days, embedded systems usually do not need this. And if they need it, they just can talk over the network to the cloud, and there is a huge storage. VxWorks also support multimedia, like accelerated graphics, accelerated computations, and so on. Nothing fancy here, just what everybody else offers. And also security is important nowadays, so even VxWorks supports some security features like secure boot, ARM trust zone, and so on. We are not going to talk much about these things in this course, but if you need it, for example, if you happen to work in aerospace industry where VxWorks is used quite often, you might be interested to know that these things are supported. So these were features. Now, which CPU architectures are supported by VxWorks? So this list is also evolves over time. So of course, Intel CPUs are supported. By the way, VxWorks is now owned by Intel, so it would be strange if Intel is not supported. The most used CPU in embedded world is ARM architecture, so this is of course supported. The new emerging architecture, which probably will be the second or maybe later even the first used architecture, not only in embedded system, is RISC-V, and VxWorks claims support for RISC-V since last year. So even in this respect, they do not stay behind. And there is something. Somebody write something. Intel or x86 in general. Yeah, so Intel, what do you mean by Intel? It's x86, but there was, for example, in the past, there was Intel X-Scale architecture, which is like, I don't know, 20, 15 years old. So this is also supported, or at least was. I don't know whether this architecture is supported by somebody. By the way, if you want to have a question, I would prefer if you just switch on your microphone and ask the question, because if I have to read it, I feel strange, like, because I have to click and then so maybe what I have here, just raise your hand. I have a list of you in front of me, so if you just raise your hand, then I will see that you want to ask something, and you can switch on the microphone and ask. It will be better for me if I hear somebody that somebody is really listening. Okay, so these architectures are supported. Yeah, so Again, no surprise, nothing unexpected here. And the most important things, at least for us programmers, is which APIs are supported by VxWorks. API means Application Programming Interface, and this is how programmers interact with the operating system. And here there are two main things supported by VxWorks, two APIs. One is well-known POSIX API. If you program for Linux or maybe other Unix-based operating system, you know POSIX APIs. So this is supported by VxWorks. But WindRiver or VxWorks offer their own API, which is called Wind API, and this is like native VxWorks API. So what is this API? How does it look like? It's a C language API. Maybe you ask why C language, why it is not something else. The answer is written here because C is portable assembler. So if there is some API for C, it can be very easily used in every other language because C is like a common denominator of all the computing. So that's it. And of course, there are some bindings for different languages they support. I don't know, like Python. Since last year, VxWorks support Rust. And probably some other language. Ada is used quite a lot in safety critical applications, so Ada is also supported. And this API is just being made accessible from those different languages, but the C API is the basis. So as I was already mentioning, it's not POSIX API, so it's not POSIX compatible. On the other hand, in some cases, it's less complicated. Some things are a bit easier in this API. For example, if you want to invoke some operation with a timeout, like if this operation does not finish within a certain time, do something. Many Wind API functions have a parameter timeout, and you can just put a number there, and if the things does not finish within the time, the function returns with an error. In POSIX APIs, it's not impossible to have timeouts, but it's much more programming, much more typing, and so on. So this is offered directly by this Wind API. On the other hand, VxWorks also offers POSIX API, and that's mainly because it's a standardized API, and basically all real-time operating systems, or if not all, then most, or at least the important operating system on the world, or real-time operating systems, support this API. And this API contains different features like asynchronous I/O and all this stuff. We will talk about all of these, so you will see later what it actually means. So this was how applications can interact with the operating system, at least the basic concepts. And now, which kind of applications we can write for VxWorks? We have already seen that in labs, that when you are starting a new project in the development environment, you have to select type of the project. And among the available types, there is a downloadable kernel module, which we have tried last week. And there is also real-time process, and we will play with real-time processes next week. And so what is the difference between those two? Downloadable kernel module, this is like a traditional application time supported by VxWorks since beginning. And it's a piece of code which runs in the operating system kernel. In the past, like many years ago, where VxWorks were started, and in 90s, let's say, of last century, it was quite common that especially real-time operating system didn't distinguish between applications and the kernel, because the boundary between application and the kernel in traditional operating system was quite costly. Like invoking a system call on these old computers, it was expensive operation in many cases, and real-time operating systems, they wanted to have like deterministic timing, and switching from the user space to the kernel was not deterministic in many cases, in many architectures, and there were a lot of weird things happening. So at the time, it was common that everything was written in the kernel space, meaning that all the code had direct access to hardware, which was very easy for programmers to interact with weird kinds of hardware which were available in like industrial settings like factories and airplanes and whatever. But on the other hand, there was no memory protection. And as you probably know quite well, if there is no memory protection, and if you use languages like C, where if you do mistake, you can write to memory wherever you want, this lack of memory protection is bad, because it can lead to weird errors or even crashes of either your application or even the whole system. And especially if the application is running in the kernel, bug in the application can lead to the crash of the whole operating system. So as the hardware evolved over time, it was clear that it's not possible to stay with this type of development even for real-time operating systems. So some, I don't know, when it was like 10-15 years ago, VxWorks started to offer a new type of application, which is called real-time process. And this is, you can imagine real-time process as a normal application which you run under Linux or Windows. This is just a normal process, and there is a memory protection. So this real-time process cannot touch the memory of other processes and cannot touch the memory of the kernel, which is good for the protection, for safety. But on the other hand, if you want to interact with some weird pieces of hardware, you need to write a separate kernel as a downloadable, separate driver or separate piece of code which runs in the kernel. So this would be downloadable kernel module, and then you need to define an interface how to interact with this, or how to interact between the real-time process and downloadable kernel module. So basically, you can see it as in the, if you are familiar, for example, with Linux. In Linux, you can write in the kernel, you can write code for the kernel as well. So this would be DKM in VxWorks. If you write a normal application under Linux, this would be real-time process under VxWorks. The difference between Linux and VxWorks is that the API in the kernel and in user space in real-time process is mostly the same in case of VxWorks. In Linux, the API is different. Another thing which I would like to mention, both real-time processes and downloadable kernel modules offer real-time properties. So the name is not that clear. Sometimes I hear from students that only real-time processes are suitable for real-time applications. That's not the case. Proper name would be real-time downloadable kernel module, because the whole VxWorks is made for real-time. So even kernel modules are made for real-time applications and for real-time code. Okay, question, yes, please.
Can you hear me?
Yeah.
I just wanted to ask if there are some operating systems which decided that instead of implementing user space real-time processes, they instead try to use memory-safe languages like, well, today Rust, but in the past maybe some other similar languages to Rust, to instead try to make the kernel modules memory-safe instead of moving to the user space?
Yes, there were such operating systems, like I would say experimental operating systems, which were not, I would say, much successful, because for things like VxWorks, where you really care about safety, because the things which are running VxWorks can kill you, it's like programming language safety is not as trustworthy as hardware safety, because hardware is much simpler than programming language. And unless the full programming language is formally verified, and unless you are really sure that there is no bug in the formal verification, which is also quite complex stuff, then it's hard to rely on it. So if you develop things for airplane, it happens like that you develop something and you are consulting that with the certification authority. And basically it means that there is some guy in the certification authority. And in the end, the guy has to say, okay, I trust you that there are no bugs, or that there are no like important or critical bugs that can kill people. And it's difficult to let's say persuade those guys that it's like this, because those guys have like many 30 years of history. They were seeing a lot of buggy programs in the past, a lot of weird buggy things, and usually what works there is that things are really simple. And if you have a complex language where the compiler has millions lines of code, maybe there is some formal verification which has again several thousands lines of code, and you are saying, and because of those 100,000 lines of code, of formal verification code, I prove that there is no runtime error. So maybe you prove it, maybe not. So it's not that easy. Of course, it's attractive, but typically people tend to not rely on a single golden feature that solves everything, but it's good if the safety is safeguarded at multiple places, and hardware is one of them. So this is I think how it is. Of course, in the future things might be different, but nowadays it's, I think, as I am saying. So hopefully the answer is sufficient.
Yes, thanks.
So these are the application types, and how does the operating system look inside? So there is one way how to graphically represent the operating system. And if you look at the picture, maybe it looks fancy, but it's like a picture that you can draw about any operating system. So there is something inside the operating system kernel. Maybe the difference from other operating systems is that you can have applications. You can have applications inside the kernel. Do you see my cursor, by the way?
Yes. Yes.
Yes.
Yeah. Maybe it would be better for me if I can show it on my second screen, but probably it's not possible. Okay, so there are things in the kernel. These are applications, but then there are standard stuff. There is standard stuff which is in other operating system, like device drivers, memory manager, some other operating system modules, board support packages, which make VxWorks run or allow VxWorks to run on various pieces of hardware and so on. And then there are separate user space applications called real-time processes here. And again, the real-time process is composed of tasks. In other operating systems, it's called threads. And those threads are running some code and work with some memory. this is basically the same as in the other environment. So from this point of view, it's a standard operating system, nothing fancy. What is fancy on VxWorks is that there are some algorithms inside or some design which is more suitable for real-time applications than, let's say, general purpose operating systems. So now we are going to start talking about different aspects of VxWorks, and I will jump like from one topic to another topic and explaining how things are implemented there and which API to use there. So the thing we will start with is task management. In other operating system, this would be threat management. But in VxWorks, everything is called task, so it's task management. So the one thing to understand is that under VxWorks, as in any other operating systems, each task is represented by a data structure inside the operating system kernel. So this data structure is typically called task context. Basically, yeah, it's a data structure. If you have ever played with Linux, even Linux has such a data structure. In Linux, this data structure is called task struct or struct. In Linux, this data structure is quite large. I think it has several kilobytes. So each thread in Linux occupies at least several kilobytes of memory for this structure. In VxWorks, I don't know what is the exact size, but probably it's a bit smaller. And there are the operating system kernel stores that the basic information about the task. So for example, what is the program counter? If the task is preempted, meaning that the task is not being executed, then where to continue with the execution after the CPU is ready to execute the task again. Then there is a content of CPU registers, is the same purpose. When the task is not running, the CPU registers has to be stored somewhere so that the execution can continue from the same state. Because the content of CPU registers, this is basically the only state or the most important state that the task has on the CPU. And if you can save and restore the CPU registers, you can switch between tasks. So this is the basis of multitasking. Then there is a stack pointer. Each task need to have a stack because this is where the function parameters and return address are stored. So this is how CPUs basically work. And then there are some operating system related functionality, like there is a timer for function delay. Maybe from last week, you remember you have called task delay function. So this task delay function uses the timer which is stored in the task context. There is time slice timer. You probably also know about what it is because we have talked about kernel time slice last week as well. And then there are other data structures which are needed by the operating system and various subsystems like device drivers there. So task context is the basis, and when you are switching between different tasks, there are you need to switch at least the CPU registers. This is the case when the tasks are running in the same address space, which means either the tasks running in the kernel, like kernel module, or when you are switching between, or not you, but the operating system kernel is switching between the tasks in the single real-time process. So the advantage of this kind of context switch is that it is fast because you really need to just to save few registers and restore the registers of the new task, and then this is the switch. But what is missing is this protection. I have already talked about that. So if the operating system scheduler switches between tasks from different address spaces, either different real-time processes or between kernel and address space, the operating system also switches the address space for the task. Basically, it means switching the pointer to the page table, which describes which addresses are accessible by the task. And here also, we will talk about that later, but VxWorks also offers implements this somehow differently from other operating systems, so that it's more efficient for real-time application, this address space switching. But even though it's implemented more efficiently, there is still some overhead with this switching. So it's even possible, if you don't want to have this memory protection, you can develop your applications with the memory protection with real-time processes, but then you can switch off the memory protection if you don't want to have it. I think nowadays it's not really a good idea, but in the past, maybe if the CPU was slow, it was good because you save some time. So it was possible to switch it off. Nowadays, I would not recommend it. Just buy a bit faster CPU and you can have memory protection. Okay, so every operating system have something which is called task states. Each task is in some state, and depending on what happens in the system and what the task does, the state changes. So this is a state diagram of the VxWorks task, and you see that whenever the task is created, it is first created in the suspended state. You can later put it into suspended state by calling task suspend or similar function. Then when the task is ready to be run, it is moved to the ready state. For some reason, VxWorks does not distinguish between ready and running states as some other operating systems do, but this is more, of course, the task is either ready and running or ready and non-running, but this is not just visible from the task state here. If the task is waiting for some time to elapse, it's in a delayed state. And if the task is waiting for something else, typically waiting for the keyboard, waiting for the network to receive some packet, or waiting for some other task, it's in pending state. Pending means like waiting for something. Typically, this waiting is implemented by waiting for a semaphore or basically semaphore. Even waiting for the network, waiting for the keyboard, waiting for these things, this is all implemented via semaphores. So the only thing which needs to be implemented is semaphore, and then things magically work. So those are the basic states. I think I have those states described here, but I have already said most of what's written here. So yeah, pending state, semaphore, message queues. If you are waiting for something, then you go to the pending state. Delay state is if you go for task delay or nanosleep. Suspended state is when the task is first created or when you call task suspend function. This is I think it's used very rarely. Normal application do not need it. And then there are some more common states like stop states, which is used by debugger whenever a task is stopped by the debugger, the task is put into the stop state. This stop state was not on the initial diagram because it would not fit there well. And then there are other things which would not fit there. VxWorks actually do not have only one state, but there are multiple states which are like orthogonal and can change independently, and this is represented as task state combination. So Maybe you remember for the VxWorks shell command I, this command printed you the list of all the tasks in the system, and there was one column representing the state of each task. So in this column, you can see those delayed, pending, ready, but you can also see there are things like delay plus S or delay or pend plus S. So this means that the task is in the delay state and at the same time can be suspended if somebody else suspended the task while being in the delay state and so on. It's not only like this, there can be other combinations like if you see plus T in the task state, it means that we are in pending state and we are waiting for a resource with timeout. Of course, you can see plus T and plus S, and you can also see plus I. Plus I means that there is priority inheritance mechanism active. We will talk about priority inheritance soon. So those are the basics how tasks are organized and represented in the operating systems and what are their states. And now let's look in more detail about the API. So the API, when you are creating the task, and we have seen that last week already, there is a function, for example, task spawn, which creates a task. One of the parameters of this function is a task priority. So VxWorks support 256 distinct priorities, where 0 is the highest priority and 255 is lowest. Beware that this priority numbering is opposite than, for example, in Linux. In Linux or in POSIX, basically higher number is higher priority. In VxWorks, lower number is higher priority. So you have to distinguish between those. Or actually, it was not precise what I have said. It's not that in VxWorks lower number is higher priority. In VxWorks Wind API, because in VxWorks you have also POSIX API, and POSIX API has the same convention as other POSIX API. Higher number is higher priority, but in Wind API lower number is higher priority. So it's a bit confusing, but it's how it is, and I think we have to live with that. Of course, you can change the priority after task is running. You can ask the current priority with task priority get and set it with task priority set. It's not a really good idea to change the priority often. In a short time, you will see why. By default, if you create a task, for example, via the IDE from the environment, the default priority is 100, and here below you can see the recommended priority ranges. So for applications, whenever you are developing applications, it is recommended that you use priorities in the range 100 to 100 to 155 for your applications. For device drivers, either your device drivers or the stock device drivers, they use priorities in those range, and network handling uses the priority 50, and there is a few more things running with priority below 50. So the reason why to have priorities like this is that for example, if you have an application with the highest priority in the system, and there is a bug in your application, for example, just an infinite loop, in real-time operating systems, it would mean that nothing else would be able to run because there is infinite loop in highest priority task. So no device drivers would be able to run, no networking would be run. Basically, this would mean that the system is dead. Whatever you press on the keyboard, whatever you send to the network, the system will not be able to react to it. So this is not. Maybe you think, oh, so okay, VxWorks, stupid operating system. If I do this under Linux or somewhere else, usually I can press some magical keyboard something and I can kill the problematic task and so on. In VxWorks, it's not like this, because VxWorks want to have deterministic scheduler. And deterministic scheduler, it means that we want to know ahead of time how and what will be scheduled. There, we don't like, in real time, we don't like heuristics like fair schedulers and these things where somehow the time is given to everybody who just wants to have time and we don't know how and when. In real-time systems, what is usually preferred is to have very simple scheduler with simple, easy to understand rule. And in most operating systems, this is called preemptive fixed priority scheduling, which is also the default scheduler used in Linux. And the only thing this kind of scheduler cares about is task priorities. So here is an example. If you have a task, a low priority task which is running, and then at some point in time, a task with higher priority is becoming ready, the scheduler just switches to this task with higher priority, because this task with higher priority has higher priority, and this is the only thing which matters. Then at some other time, there is a task with even higher priority. So the scheduler select this highest priority task, it is running. And after this highest priority task is no longer ready, maybe it is in a delayed state, maybe it's in pending state, we continue and select again highest priority task among all tasks which are ready, and so on and so on. So, and that's it. There is no other magic rule in the scheduler. Just highest priority wins, and that's it. So now maybe a question for you. So the scheduler implements this simple scheduling policy. So do you know when is actually the scheduler invoked? How does the scheduler knows that at this point in time it has to switch from task 1 to task 2? Does anybody have an idea? Maybe just start talking or just raise your hand if you wish. So no ideas. Okay.
Well, I would guess that the fact that another task is supposed to start means that there was some interrupt which caused the task to start, maybe some timeout of some hardware timer or maybe network packet or something like that. So we can just use the interrupts to react to it and switch contexts.
Exactly. That's one case where the operating system scheduler is invoked whenever there is an interrupt, like you said, timer interrupt, network interrupt, or keyboard interrupt, whatever. The operating system scheduler is invoked, and it selects the highest priority task, because it's often the case that the interrupt makes some task ready. So, for example, if a task is in a pending state, waiting for the network packet, let's say, when the interrupt comes, the task which waited for the network packet is made ready by the interrupt handler. So after the interrupt handler is finished, the scheduler is run, and if this task which was made ready is the highest priority task among all other ready tasks, then it is being switched to. And then there is another case when the operating system scheduler is invoked. Does anybody know in which other situation the scheduler is invoked? So I let's not wait. Here are the answers. So of course, if your task, for example, invokes certain system calls like task delay, because if you call task delay, it means you are telling the operating system kernel, I don't want to run now, I want to be delayed. So the operating system has to figure out who else should be run. So if you call task delay, it means the operating system inside this task delay function somewhere, it has to call the scheduler, and the scheduler then selects another task which is to be run. If there is no other task, then there is at least one operating system managed task which is called idle task, and this idle task is actually running whenever there is nothing else to run. This is the lowest priority task, and typically what this task does is it puts the CPU to low power state. So whenever the system is idle, it runs the idle task, and this idle task switches off the CPU, or at least puts it to the low power state. Okay, so this is the basic principle of the scheduler, and I think it's useful to understand a bit how such a preemptive fixed priority scheduler is implemented. So one way how to implement such a scheduler is to implement it via priority queue data structure. You can see this data structure in this picture here. And typically, this is really how operating systems implement such a scheduler. So each task is represented by its task structure. It's this box here, and those task structures are put in a linked list according to their priority. So if we have 3 tasks in the system, one task with priority 1, or sorry, 2 tasks with priority 1 and 1 task with priority 3, it would look like this. And now the question, so you know that VxWorks supports 256 priorities, like you can see here. So what is the complexity of the scheduling algorithm? What is the complexity of the algorithm that selects the highest priority task, which is the fixed priority preemptive scheduling algorithm? Any idea?
Constant with 255, because it has to go through all the buckets and figure out the first bucket where there is task that could be run.
Yeah. So the question is, what is n? If n is the number of priorities, then what you are saying would be that it's a linear complexity with respect to the number.
Yes, if I think it's linear to the number of priorities.
Yes. Okay. But this would be quite bad if operating system schedulers are implemented like that. Even if we have less priorities, it would not work very well. So in fact, most schedulers are implemented in O1, that in a constant time, the scheduler can figure out which task is the highest priority, and in constant time, it can figure out what to run next. Does anybody see how such a thing could be implemented if you have data structure like this?
It gives pointer to the highest used priority.
It could be like this, yes, but the problem then would be whenever new task is becoming ready, you would have to do this search for the highest priority. So the actual scheduling would be fast, but changing between ready and not ready state would be slow, because in this situation you would have to find whether there is a new highest priority task or not. So other ideas?
What about double linked list?
So I'm not sure I have understood. Can you repeat it more slowly?
Double linked list.
Double linked list? So how would double linked list help here? This would be the same problem as a pointer to the highest priority. So if you mean that the double linked list, that it would not be priority queue, but instead of priorities, you would have like linked list even here in the vertical direction on this picture, right?
I thought just task would be in the double linked list according to their priority.
Yeah, so it would be a list, and the list would be sorted according to the priority. Okay, so then if you imagine you have a system with 1,000 or 10,000 of tasks, then again, when the task becomes ready, you would have to sort the task to the right place at the list. Whenever the task stops being ready, you would have to put it out. So put it out would be cheap, but finding the place where to put the task would not be that efficient. So this is not the solution, or this is not a good solution. So anybody has an idea? Probably not. So
Well, there could be a main heap, but I don't think that has constant complexity. That's logarithmic.
Yeah, you are right. Then there can be some better data structure, but not everything is about data structures. The performance also depends on hardware, and maybe hardware has some tricks how to help us. So I don't know. I don't think I can draw on the slide. Maybe. Do you know whether teams allow drawing over slides somehow? Probably not. Yeah, so I know there was some way of whiteboard, but I am not experienced with that, and I don't know how to switch it on. So I will just tell it to you. So what you can do, you can have not only this priority queue, but you can also have a bitmap. Imagine a situation, for example, that you have only not 256 priorities, but you have only 32 priorities. So you have run queue with 32, priority queue with 32 slots here. And then you can have a bitmap, like 32 bits, and each bit would be either 0 or 1, depending on whether there is something enqueued into the given priority. So maintaining the value of that bit would be quite easy. Whenever you put a task into the given priority, you set the bit to 1. Whenever the last task leaves the priority, you clear the bit to 0. This is very easy to implement. It costs almost nothing. It's just single instruction. And now most CPU support an instruction which is called differently, for example, bit scan first or find first bit or something like this. And basically this CPU instruction can find a first bit in a register which is set to 1. So if we have 32 priorities, we can use this special instruction to find what is the highest priority, what is the first bit set in this register, in this bitmap, and this would directly correspond to the highest priority which is ready to be executed. So in constant time, by using this find first bit register, we find the priority, and then in second time we just dereference this pointer and we would see the task which is to be run. So we're finding the highest priority and dereferencing it's a constant time. Now what to do if we do not have 32 priorities, but for example 256? Typically this find first bit instruction, if you have 32-bit computer, this typically supports only 32 bits. If you have 64-bit CPU, it supports 64 bits, but not 256. So what you can do, you can just have 2 bitmaps. One bitmap would be for like a group of, I don't know, 16 or whatever, 16 priorities, and then you would have a second bitmap for each of those 16 priorities. So instead of executing this find first bit instruction once, you would execute it just twice, and the result would be the highest priority. So it's extremely fast. If everything is in cache, it basically means that in like 3 clock cycles, you know what is the highest priority task, and you can directly continue with switching to that task. So this is how these FIFO schedulers, how these are called, or fixed priority schedulers, are typically implemented in real-time operating systems with constant complexity. Let's wait a bit. I have to switch off the fans here. Okay, so, and remember, this was about fixed priority scheduling. Now, VxWorks offers the second type of scheduling, which is round-robin scheduling, and you probably are already familiar with that because it was the task from the last week. And this round-robin scheduling, it works like this fixed priority scheduling. Again, the highest priority wins. It's the main rule. But then there is a second rule. If there are multiple tasks with the same priority, those tasks are being, let's say, rotated in a round-robin fashion. One is being executed after the other, after a certain time quantum. And how does it work? It's very simple. The scheduler again finds the highest priority, takes the first task, and sets a timer. And when the timer elapses, this task is being put to the end of the queue, and again the highest priority task is selected. So just by putting the task to the end of the queue, you implement round-robin scheduling, or the operating system implements round-robin scheduling. The rest is the same. Yeah, so this is about round-robin scheduling and the API to switch on round-robin scheduling in VxWorks. Then let's look at some other functions which are available. There is a way how to disable scheduling under VxWorks. The function to do this is called task log. To enable scheduling is called task unlock. And in this what's called locked state, the scheduler, the invocation of the scheduler is not allowed by default. The only case when the scheduler is invoked if the active task is blocked, meaning goes from ready state to pending state. Because if the task is not blocked, if the scheduler would not be run even in this case, whenever the task would call, for example, wait for something, wait for keyboard, network, whatever, this would mean that no other task would be able to continue, and this would lead to system deadlock. So in this case, the scheduler is invoked. Also, it's important to understand that interrupts are not blocked at all in this case. Interrupts are still running, but typically what interrupts do, whenever there is an interrupt from the network, keyboard, whatever, this interrupt just makes some task ready. And the role of switching to that ready task, this is then done by the scheduler. But if the scheduler is disabled, is not executed, then nobody would switch the task. So do you know any idea what is this useful for?
When I'm doing some action that must happen in one piece and no other task should see it halfway through.
Yes, exactly. So basically you want to have you want to do something which happens atomically and you don't want to be interrupted by some other task running. Perhaps you also know that if you want to achieve this, maybe you use mutexes. So you lock a mutex and unlock it when you are done. So do you have an idea what is better, whether mutex or this task lock unlock?
Well, in case the critical section is quite short, then probably this will be faster than locking a mutex and then unlocking again.
Yes, right. I agree that it's usually faster, but this task locking has several problems, especially in case of real-time applications. It can happen that even if this critical section is very short, some important event happens and your system should react to that event. And even if this critical section is short, your system or your real-time system will not be able to react to that event because no context switch is allowed. And even if you have a task which has the lowest priority possible, and this task is allowed to lock the scheduler, then no matter how high priority you set to your task, and you will see that high priority means usually like more stringent real-time requirements. So no matter how high priority you set, you still will have to wait. And this is not good for real-time. For real-time, if we set highest priority, if there is some critical event happening, we want to react like quickly, deterministically, and we do not want to wait for any like lowest priority task, whatever who people have run. So for real-time applications, of course, mutexes are preferable than task locking, unlocking, and also soon another benefit of using mutexes is the priority inheritance mechanism, which is bound to mutexes, which also help this response time of real-time applications. We will talk about this soon. Yeah, so this question is already okay. Question? Do you have a question or no? Good. So a few more APIs for task management. So there are multiple functions which you can use to create a new task. You already know task spawn, and basically task spawn is a combination of the two above function, task init and task activate. All these functions have some parameters like task name, what is the stack size, what is the entry function, like where is the code that this task should execute, and what are the parameters. I see somebody with raised hand. Do you have a question? No? Okay.
Sorry, my mistake.
Okay. So why is task spawn not sufficient? Because in the example you have seen last week, task spawn was sufficient. Sometimes you need to create multiple tasks, and creation of task usually means allocating memory. And it could happen that you don't have enough memory for creating the task. So if you need to be sure, like in case of safety critical applications, it's often the case that when you are creating a task, it is always accompanied by some kind of sibling task. Maybe you have a task which performs some function, and then you have another task which just double checks what the first task does to have some extra safeguards there. So maybe it would be a problem if you are able to run the first task and then it starts running, and later when you are spawning the other task, you would find out that there is no memory for this new task. So for this case, VxWorks offer to split this task creation operation into two. The first task is actually allocate memory and does everything which can fail when you are creating a task. And once all these potential failing operations are finished successfully, you call task activate, and this just marks the tasks ready. So there is no memory allocation, nothing which can fail. And this way you can be sure that all the task activations or task creation will succeed. When you are creating a task, then there are these parameters, and some of those are important. So task name is not very important, but stack size is quite important. VxWorks, compared to the other operating system that you are probably used to, VxWorks doesn't allocate stack on demand. When you are creating the task, you have to specify a fixed size for your stack. And if you specify too small number, and remember, stack is used for local parameters, local variables of functions and for like passing parameters. So if you have like deep recursion or deep call chains, you might need quite some space on the stack. So if your stack size is too small, it would be problematic. The application will crash. Either it will overwrite somebody else's memory, or if it is compiled with some stack overrun protection, the operating system will just kill the application and telling the stack is too big, and you have to do something about that. It's often the case when people are, especially students, when they are programming, they forget about this. They just copy some random examples and then they allocate 1 megabyte of memory as a local variable, and then they complain that it doesn't work. The program does something different. So I'm telling you now, this could be, if your program behaves weirdly, it might be that you have allocated too small stack for your task. Now, the question is, why does not VxWorks behave as the normal operating system whenever I need to access like bigger amount of data on the stack? The other operating systems just magically allocate memory for me and it works. I don't need to care about filling stack sizes and so on. Does anybody have an idea why it is the case? Why VxWorks require the programmer to specify this number? Yes?
Because writing to that memory could have unexpected delay, or?
Writing to the memory, not, but something else.
Well, when the memory page is not yet allocated.
Yes, exactly. So memory allocation is not for free. Whenever you allocate memory, it needs to perform some operation like find the free block of memory and mark it as non-free and maybe do some other stuff. And depending on memory allocator used and how much free memory you have and so on, it might be some costly operation. And not only costly operation, but in some cases it might be fast, in some cases it might be slow. You never know ahead of time what will be the result. So to prevent this kind of timing surprises, VxWorks says, no, I will not magically allocate memory for you, because this would make your execution time non-deterministically. We will allocate the memory just at the beginning. At the beginning, we don't care about how long does it take, but once the task is running, the memory will be there and everything will be deterministic. So that's the case. Now, when you create a task, you can also specify some flags or options. One of those options is called VXFP task, and you have to specify this option when your task uses floating point operations. And again, there is a question mark. Why? Maybe we don't have too much time, so I will answer that question. The reason is similar to why you need to specify the memory size exactly. Because when again, for normal operating systems, you don't care about whether the task uses floating point operation or not. The operating systems just magically cope with whatever you use and do the right thing. But it has some cost in terms of determinism, in terms of timing determinism. Basically, what happens, remember, if you are switching between tasks, the operating system has to save the registers of your task and restore the registers of the new task. Normally, only integer registers are saved and restored. Floating point registers are not. And this is the reason is that integer registers, these are typically like maybe 100 bytes, maybe 200 bytes, depending on the architecture. It's a relatively small number, but floating point registers are much bigger. So not only that floating point register is not like 32 bits or 64 bits, it's maybe 128 bits or maybe even more. And depending on the architecture, you also have quite a few of those registers. So saving those registers and restoring them takes time. And the reason how normal operating system deal with that is that they do not save those registers. They do what's called lazy FPU switching. Whenever you switch the tasks from one using the floating point registers to another one not using them, the floating point unit is just disabled for the new task. And whenever the new task executes floating point instructions, there is an exception. The operating system handles the exception, saves the floating point registers of the old task, and restore this floating point registers of the new task. And this work like behind the scene, behind your program, automatically the floating point registers are saved and restored, but only when it is necessary. And again, if we are writing real-time applications, we don't want this, because it means that at some random point in time, the operating system might decide to save the registers and restore some other registers and doing things. And maybe it's not the right time to do this kind of thing when it is needed. So VxWorks always saves and restores the floating point registers, but only for tasks which have this VXFP task set, because typically for many real-time applications, it's sufficient to use just integer operations. You don't need floating point operations, and it's not necessary to save and restore those floating point registers for everybody. So By specifying this under VxWorks, you allow other tasks to be switched faster, and again that there are no timing surprises. But on the other hand, if you forget, and again students forget quite often, you will see some strange like floating point error or floating point exceptions and so on. So if you program anything under VxWorks and you will see strange messages, floating point something, just remember about this and double check that for all your tasks which uses floating point operations like float or double variables, you have this task set. And then there are some other flags like no stack protect and so on. These are various stack protections, things that basically protect you against stack overflow. Because if you do not have this protection enabled, again, there are some surprises with respect to the behavior of the program. It crashes and so on. So it's useful during development, but again, it costs some time. It makes your program slower, so maybe you don't want to have it always. Good. So this is how you can create tasks. Now, how you can terminate a task. So there are multiple ways how you can terminate a task. Either the task is terminated when the entry function returns. So this is like probably what would you expect it, but there are other things when you can terminate a task. There is a function called task delete. You specify task identifier, which is the value returned by task spawn or task initialize, and this way you can delete either yourself or you can delete other tasks running in the system. Because deleting other tasks in the system can be dangerous. For example, the task might have allocated some memory, do some stuff with the allocated memory, and later wants to deallocate the memory. But if you, somebody else, some else task tries to or kills the task between this allocation and the allocation of the memory, it means that there will be nobody who could deallocate the memory. So this will result in memory leaks. So for this case, it's useful to disable task deletion and enable it again. And for that, there are two functions. One is called task save and another is called task unsave. This is what you will need for this week's lab task. Probably you will need it. When you call task save, it means that when somebody else calls task delete, and this task delete will block, and this task delete will block until you again call task unsave, meaning now the terminology is a bit like weird, but if you call task unsave, it means that it is safe to delete you, or yeah, so depending on how you look at the problem, this terminology is the opposite, but basically, or maybe I'm just wrong. I would have to look it up. I would have to look it up in the documentation. One function is just to disable deleting of the task. Like before you allocate the memory, you disable deleting the task, and after you free the memory, you allow it again. And it's not only about memory, it's also useful if you work with mutexes, because if you have a mutex and this mutex is locked, and you delete the task who has locked the mutex, then there is nobody who would unlock the mutex then. So you have, it might be useful to use those functions for mutexes, and this is what you will need for today's or this week's laboratory assignment. Okay, so this was a brief introduction of task management via Wind API, this native VxWorks API. And then the same done in POSIX. Probably most of you already knows that, or at least have seen that. In POSIX, you don't have functions starting with task, but you have functions starting with pthread underscore something. And in POSIX, to create a thread, there is a pthread create. To delete a thread, there is a pthread cancel instead of task delete. It's more or less similar. The concept of task save, task unsafe is in POSIX as well, but it's more complex. It's called thread cancellation. If you are interested, you can read it in the documentation, but it's unnecessarily complex for you, I would say. Yeah, there is a link. Okay, so this was task creation and removal. Now, what else you can do with tasks? So, as we have already mentioned, we can suspend or resume task. We can restart the task from beginning. This is not very useful in many applications, but in some rare cases, it might be useful, like restart the application from beginning and so on. You can call task delay. You already know that. The strange thing about task delay is that you do not specify the time of the delay in like real-time units, but you specify it in so-called what's called system tick. System tick is basically how many timer interrupts in the system needs to pass so that the task delay finishes. So, and this value depends on the rate of the system tick. So by default, I think it's like depending on BSP, depending on the platform, it's fixed 50 or 60 hertz. So if you do task delay 1, it waits like 20 milliseconds or 18 milliseconds. If you do task delay 2, it waits 100 milliseconds and so on. And this system clock rate can be set or read by those two functions. So if you want to sleep 1 second and you want to use task delay, it's easy just to call sysclockrate get and put the returned value to task delay, and you will just wait 1 second. Or if you don't want to do this, you can just use POSIX API, which is a nanosleep function. This is the same as under Linux, and there the calculation conversion between system ticks and physical time is already there. But don't be confused. Nanosleep, it suggests that maybe you can sleep 1 nanosecond or maybe 10 nanoseconds. But under VxWorks, the resolution of those sleeps is always the system tick. So if you do nanosleep 10 nanoseconds, you will always sleep until at least the next tick, which might be in few nanoseconds, but it might also be like 20 milliseconds if you happen to call it just after the last tick has been finished. Okay. Yeah, so POSIX API, about the numbering of priorities, we have already talked about that. In POSIX, different processes can support different scheduler. Under VxWorks, this is one of the few things where VxWorks are not fully compliant to POSIX under VxWorks. Even POSIX API forces the same scheduler to all the processes. There is simply just one scheduler common to all the processes. POSIX API, just very briefly, you have already heard about that. Probably in POSIX you can select the scheduler by calling scat_set scheduler function. And you specify the policy, and the scheduling policy can be either scat FIFO, which is this preemptive priority-based scheduling, or scat RR, which is the round-robin scheduling. In Wind API, you select between those two with this kernel time slice. In VxWorks, there are only those two. Under Linux, the default scheduler is this sched_other, which is this kind of fair scheduler, which tries to be fair to all the tasks in the system. But in VxWorks, this sched_other probably means this is the same as sched_FIFO. What next? You can set the priorities with and other scheduling parameters with POSIX API. With those functions, you can set the round-robin interval or get the time round-robin interval with sched_RR get interval. In POSIX, you can call sched_yield. Sched_yield basically means, if you remember, let me see. It is not here. If you remember this task structure, so sched_yield means put the currently running task, put it at the end of the queue. So if there is multiple tasks of the same priority, sched_yield just gives the CPU to other tasks of the same priority. If there are other tasks, if there are no other tasks, if there are no other tasks, schedule just does nothing. So I have lost my current slide here. Good. What next do we have? Yes, scheduler invocation. We have already covered that. Good. What is the context which we have also covered that? Yeah. So I think we are more or less at the end of what I wanted to say today. So we still have a few minutes. So I will just try to ask you the question which is here on the slide to just understand whether people have listened to me or not. So can somebody tell me what is the context switch, what happens at context switch, and so on? Maybe it's trivial question, maybe not. So what do you remember? Okay, nobody want to answer, so I will ask you an exercise. Just to repeat, context switch basically is saving the registers of the CPU to the context of actually running task, finding the task with the highest priority, which will be run next, and then restoring the registers from the context of that new task, putting that to the CPU registers, and just continuing the execution based on the program counter. That's it. Do you have any questions related to either today's lecture or to any organization stuff, like you cannot attend, you cannot see something doesn't work, or whatever? Good, no questions, perfect.
Just the deadline for the homework is tomorrow, yes?
Yes, the deadline for the homework is tomorrow. For today's exercise, it's I think tomorrow. For tomorrow's exercises, it's on Friday. But the idea is that you will like explain the teacher what you have found. So it's not sufficient just to submit the task somewhere, but you have to tell the teacher like what you have found and how does it work. So just do it at the exercise. There will be time for this.
Okay, and I have a question. How many licenses do we have? Because I'm still troubling with the connect on Wind River to run anything because there is no more licenses.
Yeah, so it should be better this week, hopefully. We have 20 licenses. And the thing is, and I think we will repeat it at exercises, but it's good that you ask because I can tell it so that everybody hears it. When you finish your work with VX works, just do not simply I don't know, unplug your computer from network or whatever. Just shut down at least the development environment or the whole remote desktop, because if you leave VX works or this development environment running, it means that it periodically asks for the license, and there is no enough licenses for other students. So just switch it off. In some cases, I can kill your stale sessions, but I'm not sure whether it works reliably. So if you do it, it would be better. And if you have problems, or other way around, if we have problems with these things, we will just be killing all the people's session at the beginning of each exercise, meaning that if you are working on your solution with while there is another lab running, we will probably kill you. So please respect that there are other classes running, and try to work at the time of your class or at the time of where there are no other classes. I know it's annoying if it will be. So far, it has never been problem when we worked with physical computers. So maybe if it is problem this year where people work remotely, we will try to increase the number of licenses, but it will take few weeks typically, and so at least now we have to live with what is now. Good.
Excuse me?
Yes?
One last question. When you were talking about the homework before, do you mean the homework for the exercise classes, or in this class that we are right now? Because I think in the exercises we have another teacher.
Yes, homeworks are only for exercises. And yes, you have another teacher, but it will be similar for both teachers, like for me and for the other one. We try to synchronize and try to do things similarly. So it should
okay, yeah.
apply.
This sounds good, because we also had another homework from the last week, and I thought that you were talking about another homework, but it should be there for the same homework. Yeah.
Yes.
Okay, thanks a lot.
You're welcome. Udělá nějaký divný zvuky, nevím, jestli někdo se snaží mluvit, nebo ne. Dobře, tak zdá se, že...
if I may ask one thing, I'm not sure how do we close the remote desktop session. There's no how to do that.
Okay, good question. So I think I will show you, and the other teacher as well, how to do it on your class. The easiest way, if you have this Xpra client, there is some menu for it. Typically, it's in a system tray, like there are those icons of the programs running in background. So there is also icon for this Xpra client, and there are two menu options. One is disconnect, and one is shut down server. So if you do disconnect, which is probably the same as if you just close the window, it closes the window, but the server session is still running. So you have to click shut down server, and it means that it will shut down things on the server, and also, of course, also disconnects your client.
All right, thank you.
Good. So it seems no more questions. We can continue with my exercise in few minutes, or tomorrow with the other teacher. So thank you and goodbye.